Hi everyone, today's lesson is going to entertain the idea of limits approaching positive and negative infinity with a little twist of lemon here, a little absolute value. So the first thing we're going to do in this lesson is revisit the definition of absolute value. So let's take a look at this. The definition of absolute value, I'm not sure if you've ever done it this way, but I'm sure you have, but absolute value of x can actually be written as a piecewise equation because there are sort of two conditions that have to be thought about to define absolute value. So let's think about it. The absolute value of x. Well, you know that the absolute value of a positive number is equal to itself. So I'm going to say the absolute value of x equals x if, so long as this x that you started with is greater than or equal to 0. So what this is saying, the absolute value of a number that's positive is itself x. Now on the flip side of that, the absolute value of x is equal to something if that x starts off in the bars negative. Okay? So if the x that's in the bars starts off negative, then we have to think about this. Let's just actually look at an example. So if I'm doing the absolute value of -5, well, we know that the absolute value of -5 is positive 5. The only way we can get that is to take the opposite of that -5. So you take the opposite of what you started with, and that gives you the answer 5. So what's interesting is this notation right here and this notation right here essentially mean the same thing. One has the absolute value bars, which is going to shoot you out to 5. One does not have the absolute value bars, but still the opposite of a negative is a positive. So the way I'm going to define this over here is that if the x starts negative in here, then the answer is the opposite of that negative number. Now this will wig students out a little bit because they'll say to me, Ms. Callahan, okay, so I was always taught that the absolute value, the answer is a positive. How can we have a negative here? And the response is, well, remember, in this part of the piecewise function, this x, this is a negative number because of the domain here. So I'm taking the opposite of that negative number. So this whole expression is actually this positive number. So just to make sure. So when you're doing a limit to infinity, the whole idea is if the limit has absolute value bars, you want to use this definition to get rid of them. You can do absolute value without the bars by simply following your definition. So let's take a look at our first example. Okay, so example 1 says we're going to take the limit as x approaches infinity of x divided by the absolute value of x plus 3. So just like with any limit, the first thing we're going to do, actually no, I lie. We were going to plug it in, but I think we'll reverse that. I think what we'll do here is we'll go with this idea. When you have a limit and there are absolute value bars, let's just work right off the bat to get rid of those absolute value bars. We basically don't want to do a limit with absolute value bars in it. So let's take a look at our definition and the limit. So let's look here. X is approaching infinity. Okay, that means x is a really, 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 really large positive number. Now we eyeball our absolute value piece. It's the absolute value of x. So let's pick some really, really large numbers. Let's just play around. This is called play around over here. This is math play. So say it's 100. Say x is 100. The absolute value of 100 is itself 100. The absolute value of 5,000, itself 5,000. Any positive number is going to have an absolute value, let's look up here at the definition, equal to itself. So because the x is approaching large positive, having those absolute value bars there is the same as not having them there. But that's only because x is greater than or equal to 0. See how infinity lies on that domain? So I can actually rewrite this problem like this. The limit as x approaches infinity of x over x plus 3. See, I just dropped the bars. I dropped the bars because x is large positive. Perfect. Now we just go about our business like we did yesterday. So the first step in the recipe to a limit at infinity is to plug it in. So if I plug infinity in for these x's, I'm going to get infinity over infinity. That's undefined. So I'm going to divide each term of my rational function by the highest power of x in the denominator. That's x. So this step will give me x over x all over x over x plus 3 over x. And when I reduce it, that's going to give me the limit as x approaches infinity of 1 divided by 1 plus 3 over x. And now when I plug my infinity back in, I have 1 over 1 plus 3 over infinity. My 3 over infinity is heading toward 0. 1 divided by 1 plus 0 is 1. So the answer to this limit is 1. See how easy that was? Okay, let's go to example 2. Example 2 says, same problem, same rational function, but this time look where we're headed, negative infinity. Okay, so the limit as x approaches negative infinity. So let's go off to the side and play. Let's pick some really, really small numbers for x and see the effect it has on these bars. So say we're doing the absolute value of negative 100. Well, we know that the absolute value of negative 100 is 100. But let's do an intermediate step because of this definition up here. If x is a negative, then the absolute value is equal to the opposite of that negative. So the intermediate step here would be to take the opposite of 100. I'm sorry, the opposite of negative 100. And that is positive 100. So we need to focus on that intermediate step. This step has the same effect on this answer as this absolute value does. And if we do the absolute value of negative 5,000, well, that's the opposite of that negative 5,000, which is positive 5,000. See, we can go from here to here or from here to here. These two are the same. So, coming back to my limit, if I want to get rid of these bars, but I want the problem to remain intact value-wise, like I don't want to change the problem, the only way to have the same effect that these absolute value bars have is to change the absolute value of our negative number into the opposite of that negative number. I'm going to make this switch right here in my problem. So it'll look like this. The limit as x approaches negative infinity of x over, you ready? Here's the switch. Opposite of that negative x plus 3. And this is only because my numbers inside are negative. The rest is history. If we plug it in, if we plug negative infinity in now, we have negative infinity over positive infinity because the opposite of negative infinity is positive infinity. That's undefined. So now we will divide by the highest power of x in our denominator, which is x. So x over x divided by negative x over x plus 3 over x. When I reduce, I get the limit as x approaches negative infinity of 1 divided by negative 1 plus 3 divided by x. Plug in negative infinity back in, and I have 1 over negative 1 plus 3 divided by negative infinity. This guy approaches 0. So 1 divided by negative 1 is negative 1, and that is the answer to this limit. Okay, let's take a look at one more. Example 3. Limit as x approaches infinity of the absolute value of 9 minus 3x squared all over x minus 2x squared. So again, draw your eyes to where the bars are. I want to get rid of those bars. I don't want to do a limit with absolute value bars. So let's play. Okay, well, let's see what x is approaching. The values of x we may plug in during the playtime are large positive. So let's put 100 in there for this x. So if we take the absolute value of 9 minus 3 times 100 squared, let's see what we get. depending on what you used, you might need your TI. So if I take 9 minus, oh, not that, 9 minus 3 times 100 squared, I get negative 29,991. Okay, this is the absolute value of negative 29,991. We know the absolute value of this negative is positive. The intermediate step, of course, would be to take the opposite of that negative, which will turn it positive. So what we found is that when x is large positive, this guy right here is a negative, so we must take the opposite of him to get the correct answer. Okay, let's pick another large positive. Let's pick 5,000. So let's do the absolute value of 9 minus 3 times 5,000 squared. All right, 9 minus 3 times 5,000. The second power is, whoa, that's a big number. Absolute value, negative 7499991. Okay, there's my number. It's huge negative here, or small negative here. The absolute value is positive. The only way to get there is to take the opposite of this negative crazy big number, which will give me the positive. So, through the math play, what we realized is this. In order to get rid of these absolute value bars, but have the problem remain intact value-wise, is to drop them, remembering that no matter what large x we put in here, the result inside will be negative. So we have this part of the definition. The absolute value of a negative is the opposite of that negative, the opposite of that negative. So I will drop the bars, replace the opposite of this negative number right here, and go on my merry way. What I like to do here once I drop the bars is distribute. So I'll have the limit as x approaches infinity of negative 9 plus 3x squared all over x minus 2x squared. When I plug infinity in by principle of dominance, I'm going to get infinity over negative infinity. That's undefined. So we're going to divide each term by the highest power of x in the denominator, which is x squared. So I'll have negative 9 over x squared plus 3x squared over x squared over x squared minus 2x squared over x squared. When I reduce, this guy will stay negative 9 over x squared plus 3 divided by 1 over x minus 2. When I plug my infinity back in, I'm going to have negative 9 over infinity squared plus 3 divided by 1 over infinity minus 2. This will go to 0, this will go to 0, and I'll be left with negative 3/2, and that is the answer to this limit. Last thing, please write down the definition of horizontal asymptote that I have here. It says y equals b is a horizontal asymptote of y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. This is something we're going to use in a little bit, but it'd be great to have it in your notes today. This is the definition of horizontal asymptote. So these limits we've been finding to infinity, the answer we've been getting, negative 3/2, negative 1, and 1. Yep, that's a horizontal asymptote. So pause this video and write that down. Okay, that's all.